This video, we will talk about a very important notion in statistics and probability. It is conditional probability. The very important concept in probability theory is conditional probability. In some applications, the practitioner is interested in the probability structure under certain restrictions. For instance, in epidemiology, rather than studying the chance that a person from the general population has diabetes, it might be of interest to know that this probability for a distinct group such as Asian women in the age range of 35 to 50 or Hispanic men in the age range of 40 to 60. So this type of probability is called a conditional probability. So the probability of an event B occurring when it is known that some event A has occurred is called a conditional probability. So we denote conditional probability in the form as probability P bar A B, which means the probability of B given A is occurred. So both B and A are events. We take a look at an example of conditional probability. So for example, consider the event B is getting number 4 when a die is tossed. So usually if a die is a balanced die, each number will have the same probability to occur. So 1, 2, 3, 4, 5, 6, right? But the die is constructed here so that the even numbers are twice as likely to occur as the odd numbers. So based on the same sample space S equals 1, 2, 3, 4, 5, 6. So with the probabilities of 1 of 9 and 2 of 9 assigned respectively to the odd and even numbers, because the total probability of those sample space should be equal to 1. So 1, 3, 5 each occur with a probability of 1 of 9 and 2, 4, 6 with 2 of 9, right? So now suppose that it is known that the toss of the die resulted in a number greater than 3. So this is the probability of A given greater than 3. So we are now dealing with a reduced sample. A equals 4, 5, 6. So this is called a reduced sample because we only consider under this condition, because this is the condition A occurred. So probability of B given A, so we considered reduced sample in the A. So which is the subset of a sample space, total sample space is S. So the probability of B given A occurs is 2 of 5, right? B is getting number 4. So because 4, 6 each equals 9 or 2 of 9 and 5 probability is 1 of 9. So from this reduced sample, the 4 occurs, the probability is 2 of 5, right? But we can also use another idea, which from the sample space S, the total sample space. So probability B given A can be written as probability A in the denominator and the probability of both A and B occur in the numerator. So this is the more formal form of the conditional probability. The conditional probability B given A denoted by P B bar A is defined by PA in the denominator and PA intersection B, or PA and B both occur in the numerator, the division of these two parts. So where A and B and PA are found from the original sample space. So if we use this form, both the numerator and denominator can be found from the original sample space S, not use the reduced sample. So in other words, a conditional probability relative to the subspace A of S may be calculated directly from the probabilities assigned to the elements of the original sample space. So actually PA is like a reduced sample, right? So we take a look at another example. Suppose that our sample space S is the population of adults in a small town who have completed the requirements for a college degree. And we shall categorize them according to gender and employment status. So this is a contingency table with the rows for the gender, male, female, and column for job status, employed and unemployed, and with the field to represent the counts for each category. And this for the marginal for the column and the marginal for the rows, and this is the total counts. And one of these individuals is to be selected at random for a tour throughout the country to publicize the advantages of establishing new industries in the town. We shall be concerned with the following events. So the event M means a man is chosen. Event E means the one chosen is employed. So using the reduced sample space, if we use the reduced sample space method, we find that probability M given E, so which means the person, if we know this person is employed, the probability of he is a man, right? So we have to choose from employed sample space. So this, if we use the reduced sample space, so this is the reduced sample space because there are totally 600 people employed. If we look at the previous table, so employed columns are totally 600 people employed. So from these 600 people, 460 are men. So this is the reduced sample method. So we can directly divide 460 by 600. So from these employed people, there are about 23 of 30's probability will be a man. And if we use more formal calculation from the definition of conditional probability, we can let NA denote the number of elements in any set A. Using this notion, since each adult has an equal chance of being selected, we can write PME equals NE in the denominator, and N means number counts, E and M, both E and M occur. So if we divide these two by NS total sample space, which means the probability of E in the denominator and probability E and M in the numerator, right? Both P, E, M, and P are found from the original sample space here. So we go further, can get PE equals employed equals 600 divided by 900 equals 2 of 3. And PEM, both, so the person is employed and person is a man. So this means the probability is 460 divided by 900. So equals 23 of 45. Then we fill these two numbers into conditional probability. We get the same result as using reduced sample method. Another example is the probability that a regularly scheduled flight departs on time is PD equals 0.83. So PD means the departure at regularly departure on time. So PD means departure on time. And the probability that arrives on time is PA equals 0.82. So PA means arrives on time. And the probability that it departs and arrives on time is PD and A equals 0.78. So find the probability such a plane first arrives on time given that it departed on time. The B question is find the probability of a plane that departed on time given that it has arrived on time. So the solution is, if we use the definition for the conditional probability, we can have the following. For the first question, the probability that a plane arrives on time given that it departed on time is just probability A given D. So probability of arrived on time given it is departed on time. So the departed on time's probability is in the denominator and P, D, and A in the numerator, right? So we just follow the definition of the conditional probability, PD in the denominator and PDNA in the numerator. So the result is about 0.94, means if we know that the plane departed on time, then it will get arrived on time about 0.94 chance. And the second question is the probability that a plane departed on time given that it has arrived on time. So in this case, it's just P, D given A. So P, probability of arrived on time in denominator and probability D and A in numerator is about 0.95. So which means if we know that the plane arrived on time, then it will get departed on time about 0.95 probability. So in this example, we know that the notion of conditional probability provides the capability of re-evaluating the idea of probability of an event in light of additional information. That is, when it is known that another event has occurred. The probability A given B is an updating of probability A based on the knowledge that event B has occurred. So if we do not know how it's going with probability B, so we only know probability A, right? But if we has additional information of probability B, then in this case we know probability of A given B. So this is an update of the probability of A in the light of additional information. So for example, if one is given the information that the flight did not depart on time. Armed with this additional information, one can calculate the more pertinent probability of arrived on time when departed not on time. So this is very interesting question because we want to if we only know probability A is not enough. But now we get information that departure is not on time. So we want to know this case, what is the probability of A arrival on time? So how to calculate this? So the probability that it arrived on time given that it did not depart on time is computed as not depart on time in denominator and probability of arrive on time and not depart on time in numerator. So not depart on time is just calculated with the 1 minus PD, right? So it's 0.17 because PD is 0.83 in this example's information. And the PA and D quotes what means this is arrival on time but depart not on time, which means if we look at the information, so PA is 0.82, PD and A is 0.78. So if we minus PA minus PDNA, then we will get the probability of PA but PA and D quotes, right? So PA arrival on time 0.82. In this arrival on time, both D and A occur is 0.78. So if we minus this one with this one, then we'll get probability of A and D quotes, which means arrival on time, departure not on time. So numerator is 0.82 minus 0.78, so about 0.24. You can see the probability of arrival on time is diminished severely, only 0.24 probability. If we note additional information such departure not on time. Thanks for watching.